Now let's look at for this case of a series solutions near infinity. For example, we have this differential equation, and the question is for x near infinity, find the first three non-zero terms. So for x near infinity, first we have to let z is equals to 1 over x, because when x is approached to infinity, we'll have 1 over infinity, so we have z is equals to 0. Therefore, that's why we have to let 1 over x is equals to z. Hence, we have to change for every x here in terms of z. So to change that, since z is equals to 1 over x, now we'll have x is equals to 1 over z. But before that, in our equation here, we have dy dx and d2y dx squared. So when we want to change every x into z terms, therefore this dy dx also will have to change into dy dz. Now, since we have z is equals to 1 over x, therefore our dz dx, when we differentiate z respect to x, so we have negative x to the power of negative 2, and this is also equals to negative z squared, because 1 over x squared is equals to negative z squared, because 1 over x is equals to z. Next, we want to find dy dx. So dy dx is equals to, by using chain rule, so we have to fill in with dz. If I can rewrite it as dy dz, so we know that our dz dx is equals to negative z squared. dz dx equals to negative z squared. So substitute in here. So this is our dy dx. Next, we want to find d2y dx squared. So to find d2y dx squared, we have to differentiate dy dx again with d dx. So we want to differentiate with dy dx with d dx. So we know that our dy dx, just now we have negative z squared dy dz. Again, by using chain rule, this d dx here, we can write it down as dz. And then we want to differentiate. So if we differentiate this, since this is a product function, we have two functions, negative z squared and dy dx. So this, we have to use product rule. Alright. Okay, what I just did here is by using by using product rule. So this is our u, this is our v, u v prime plus v u prime, and then our dz dx here is equals to negative z squared. So we'll simplify this. This is our d2y dx squared. Now back to our question, we want to find this we want to solve this equation. So we have to substitute everything that we have done of our x into 1 over z, and d2y dx squared and also dy dx with we have just shown earlier. So by just substitute, after we substitute, we have to expand and simplify it. Again, we can simplify with 4z dy dz minus 3z. Okay, so this is our new differential equation. As usual, if we want to solve this differential equation, first we have to identify our P, Q, and R. So in this new equation, our Pz is equals to 2z squared, our Qz is equals to z, and R equals to negative 3z. Again, since our z is equals to 0, so P0 is equals to 0. Therefore, z equals to 0 is a singular point. So we have to identify either this will be regular or irregular. To show that this point is a regular singular point, so we have to use the two conditions. The first one is limit of z q over p, which is z over 2z squared as z approach to 0, so we have 1 over 2. And the second condition, limit of z approach to 0, z squared multiplied by r over p, which is negative 3z over 2z squared, and we have is equals to 0. So since both limits are exist, therefore z equals to 0 is a regular singular point. We have to solve this equation as a regular singular point. So for regular singular point, y equals to a n x, we have to use z, n plus r. Same with y prime. So our y prime here is our dy dz, okay? It's not dy dx. Now, since we have our y prime, and y double prime, substitute again into our new equation that we have gotten earlier here. After we substitute, we have to expand. Next, we have to equate z to the smallest power, which is z to the power of n plus r, okay, to the smallest power n plus r. So we have to change this, we have to shift this to be z n plus r. So the changes here is n equals to 1. We have to change for every n equals to n minus 1. Now we want to find the initial equation for n is equals to 0. For n equals to 0, so we'll have to focus on this part here, because here we have n equals to 0, but here n starts from 1. Therefore, we'll just use this part. And then when we expand, we have, so we can say that 2r squared minus r equals to 0, but an cannot be 0. So the initial roots for r is equal to 0, and also r equals to 1 over 2. So we know that this will be our case 1, okay, because for r1 minus r2 will not be an integer, a positive integer. So we know that this is our case 1. Next, we want to find a recurrence equation. Okay, we want to find our recurrence relation for an. So we'll simplify this. You can just stop it here, or you can also simplify it as now. For the first r1, for our first root, r1 is equals to 0. So our an will be 3an minus 1 over 2n squared minus n. When n equals to 1, so we have to find for a1 and a2 because we want the first 3 non-zero terms. So for a1 equals to 3a0. Next we want to find a2 for n equals to 2. So a2 is 3a1 over 6, or our a1 is 3 over 6. a1 has become 3a0. It's equals to 9 over 6 or 3 over 2 a0. So now we have our a0, a1 and a2. Therefore, we'll have our y1, solution for y1 is equals to, or we can, since x power of 0 equals to 1, therefore our y1 a0 plus a1x, a2x squared, and so on. So by substitute, sorry, those are not x, they should be z. Okay, so we have substitute a0 plus a1. Our a1 here, a1 is equal to 3a0, z plus a2 is 3 over 2 a0 z squared, and so on. Or we can factorize a0 if you want. So 1 plus 3z plus 3 over 2 z squared. Finally, we have to change our z as 3 over x, as 1 over x. So we have 3 over x plus 3 over 2x squared, so on. So this is our first solution. Next, we have to find our second solution for R2. For R2 is equals to 1 over 2. Again, by substitute into this our recurrent solution, R equals to 1 over 2 here. So 3a and minus 1. So repeat again for n equals to 1. So a1 equals to 3a0 over 2, so equals to 3a0 over 3, which is equals to a0. Same again with n equals to 2. Okay, so we can find our y2, which is a n z n plus 1 over 2, or we can put it z 1 over 2 here. So by expanding this, we have a0 plus a1z a2z squared, and then we substitute with our finding above here. a1 equals to a0, a2 is 3 over 10 a0, and finally we have to change z with 1 over x. So we can factorize a0. Z is 1 over x, so 1 over x power of 1 over 2, 1 plus 1 over x. So these are our two solutions for y1 and y2.